Something really valuable about actually attending and being here in person is having the opportunity to actually ask the speakers while they're there, go up to the microphone, ask a question that you have, or meet them after the talk, chat them up in the hall. There's just a lot of opportunities if something isn't really clear to you to kind of just get in there and get a much clearer answer if you need one.
Good afternoon. Let's discuss a little bit about the networks in the context of any particular programming language, and in this case of C++. So, what it is all about. First, talking about the networks, quite often I do get such a fine request. Can I please have something that decreases my latency immediately to 0, increases my bandwidth, reliability, and everything just works and gets out of the way? Well, sorry, that thing doesn't exist. And that basically concludes the session. That's it. It's against the laws of physics. Right, jokes aside, this is an introductory attempt to explain about what is happening in a contemporary network transport protocols, how is that evolving, how that is starting to cause all sorts of performance, complexity, and general application and awareness of the network type of problems, and what can be done from a perspective of the language. So to set the context of the discussion. The main assumption is that the topic of networks is generally seen as a second-class citizen. Well, and that's just a pipe, it sends packets from left to right. And what happens there, operating system or some underlying platform provides you some interface, you use that, and you don't basically look into any more of the details. What if we thought about revising the 40 years old BSD sockets API or Win32 API, which mostly clones it, for the reason that over the last decades we have seen quite a lot of development in new transport protocols, and while they bring in the new functionality, in order to use that and basically to try to model it on top of the existing network interfaces, there are two sorts of limitations. One is it becomes inherently difficult to bring in the new functionality. Second thing, it puts in the complexity into your application, because the interface that has been standardized 40 years ago does not necessarily fulfill the possibilities that could be achievable with the new transports. If anything to define, this is the work for a library part of the C++. There's no attempt to define any new language constructs. There's no attempt to define yet another concurrency framework. And what would be important is in defining this library interface to basically have that able to use already existing concurrency frameworks that are already present in the language in a way that doesn't obstruct the new functionality available in new transports. One comment about inventing yet another protocol. Certainly that's huge fun. Well, I myself have done that quite a few times and I really enjoyed it. The only aspect is that if we are talking about a global end-to-end connectivity, that's one scope. It has to interoperate globally. If we are talking about the limited domains, basically your own infrastructure, you're free there to do whatever you want, and including defining the interface to your new transport protocol. Therefore, for that environment, this talk probably won't be of much interest and value. Why would you want to define a new specialty transport? Generally, if you are large enough and relying on the network infrastructure substantially, a network is not just a dump pipe for you, you might see a lot of benefits in trying to cut out one message or a few octets or reassigning a few bits in the header for achieving the functionality that might be critical for your use cases. However, that is definitely not for everyone. That's not for the commodity end-to-end communication case. So there are a few parts in this talk. First one is the interface into the transport. It's about communicating between the two applications running on two hosts, generalizing whatever the host means. Again, network is a dumb pipe. You put something on one side and you hope that it will show up on the other side. It may show up, it may not. It may require additional effort to try to control what shows up and at what instant in time. Let's look at the existing protocols from the perspective of the requirements, what they would bring to a common transport interface. So TCP, absolute commodity, models the logical session, internal state, TCP control block, which has the basically internal representation of what is needed at an endpoint that might be visible for your application depending on your operating system, depending on your interface. The problems that start to be evident with the BSD sockets interface into the TCP starts from a no operation type of thing. Suppose I want to do a keep alive type of transport connection. Well, basically that the middle boxes don't time it out for keeping it visible in some, say, monitoring system or something like that. I actually cannot easily do that on a data plane because there is no concept of sending 0-byte message with TCP. Yes, there are options that are available via basically get-sock-opt to indicate that I want on this session to have a certain keep alive, which sends out a specific internal TCP message, which is not externally visible, and that will keep the state. But if I want to have that from my application, saying I don't have anything to send, but I want to send an indication that I'm still alive and I'm still there, there's no such easy possibility. You need to do that as an exception to your normal data processing. If you start to look into the MTU, path MTU, and basically what you can send out without requesting additional fragmentation, that also is not necessarily visible. Yes, you can query what is the current path MTU on this connection. If your underlying network, for example, triggers reroute or some other form of protection and adds another MPLS label onto the stack, your MTU decreases by 4 octets. This might come as a surprise if you assume that your current MTU is still the same. There's no easy way to get a notification of the path level parameters, again, as a common interface. It's possible to query that, but again, that is seen as an exception. Authentication options, quite a few. They address the real-world problems, basically preventing the replay type of attacks on a session and middle boxes. But in order to enable those, once again, you need to use specific socket option. This is per socket option. TCP MD5 allows you to set the key only at the session setup, and while technically you can change it by doing some fragile coordination between the both endpoints, that is something that is not necessarily too reliable. Authentication option allows you to change the key, but again doesn't specify the say interoperable interface, how that could be done. And if you happen to support multiple operating systems, they do that in a very different way. How the keys and algorithms for authentication are used, again, the protocol says that you can define the values. How you do that, it's up to you. So it's an open question for what the interface, what a common interface could be for that. Fast open, if you care about the latency, you actually can send a payload with the initial scene packet of TCP session establishment. Again, that is not your regular data interface. You need to do that as an exception. And TCP has a really versatile and flexible congestion control mechanism. The problem with that is that, again, the internals, both the internal state and the parameters that can be used to control that are not directly accessible to you. Yes, you can get that, again, platform specific or via certain socket options and extensions, but that, again, is an exception path. So where I'm coming to, It would be probably really nice if we had something like a common interface which can be used both for the data operation, feeding basically the data that needs to be transmitted and getting notifications that are received, and at the same time getting the information about the dynamic properties of the TCP session in one more or less uniform interface. Let's add some complexity, multipath TCP. Well, basically the idea is very simple. You have multiple connections in parallel. They still provide you the sequenced and reliable guarantee of transporting between the endpoints, but there are multiple sessions. This helps both with capacity, this helps both with the resilience. You can do, such things as use IPv4 and IPv6 at the same time and still treat that as one single logical session, well, if you would have a use case for that. Again, congestion control is different here because you also need to look into the interoperation between those two subsessions. From a logical point of view, from what the application sees, that's one logical transport connection, but its operation properties are different and the tuning might be different. Again, we need specifics how to export and be able to adjust that information. UDP, another absolutely universally deployed transport, simple, just send out something and hopefully it shows up. If it doesn't show up, you actually have no simple means to know that it didn't show up. And some form of indication about that would be beneficial. Congestion control is left for the application. However, it might be of value to have some indication into the lower properties of the path, because you know the endpoint where you are connected to, and you can query, for example, what is the path MTU available there. Again, the current interface does not allow that to do in a simple way. UDP Lite, that's actually quite a niche transport in a sense. UDP which has a shorter checksum and part of the payload is not covered by the checksum. That works perfectly fine for lossy data, think audio channel or some other media over the radio link. Radio link might have its own forward error correction, or you simply don't care too much about errors in the payload because your codec will compensate for that. The headers are still protected. Again, we need the UDP Lite defines a slightly usable error interface, saying that I have received the packet with broken checksum, therefore it's up to you to decide what you want to do. That's good. TLS, likely the dominant part of the global traffic today. However, that's not a standalone protocol. That's basically a stack. You have TCP below, and you have a couple of layers of specific subprotocols for exchanging the security-related parameters and actually transforming the data that is being sent between the endpoints. The implementations of TLS are plenty. They do that in different ways, and they tend to use OpenSSL defined interface. Some have their own proprietary ones, but the most common one is OpenSSL based. And this gives a large set of problems in event handling. The TLS library implementers have their own view about event handling and how to export that to your application. And sometimes those views might be radically against what you think about the event handling. So while it does provide a definitely required interface into simplifying all of the security credentials handling, well, you basically feed in a certificate in one form or the other, and eventually the session shows up. But actually handling the data, both sending and receiving from that, you are very much controlled and restricted by what that particular library's author thought about what is a good event handling. You cannot just pull on that socket anymore because there are transit layers that need to be peeled off before that data gets sent to your application. DTLS, exactly same idea implemented on top of datagrams in UDP in this case, with one addition that it implements its own kind of pseudo-reliable transport, pseudo TCP in the sense of adding the sequence numbers, but from the interface perspective, it has the same problems. Basically, event handling is complicated and depends on a particular library. Stream control, that is a specialty niche protocol typically used in mobile wireless control planes. It was specified, started being specified since long, and it still stays there. It has interesting properties. It has been designed with reliability in mind. So, for example, it addresses the TCP's problem of unreliable closure of a session. With SCTP, you actually get a definitive notification that the session has been closed and for the reason this or that. Whereas with TCP, it might end up that if the remote site ended the session, you might still think that it is available until you actually try to use that. CTP defines streams, so basically subchannels, and it allows to carry objects or actual payload concurrently. It guarantees ordering within a subchannel, and actual subchannels can be processed concurrently. There are different extensions with different restrictions of what is available and how. But from the interface perspective, you don't have one socket or file descriptor anymore. You have something else which has logical separation. And how that maps on top of a BSD sockets, again, is not clearly defined. And generally, it depends on the implementation. A couple of popular implementations model that based as an ancillary data. Same things that you use, for example, for gathering the UDP socket destination source information. You use that to gather here or to move a file descriptor from one process to the other. Works. Again, that is seen much more as an exception than the, say, commodity interface. RDMA over converged Ethernet, that's in the domain of the high-performance computing. So InfiniBand defined its own transport, and on top of that, it defined the mechanism to transport a page or a buffer from one address space to the other as a message. Quite a complicated protocol and very different than the IP world. But what they did right there is in the asynchronous operation mechanism. Basically, there are multiple queues, the queue for transmission, the queue for reception, and the queue for completion. You send out a descriptor saying from that address, that many pages, send over there. And then the library actually will do that behind you for the actual transmission. When somebody sends something to you, you will get a notification saying that there is the descriptor waiting for you, and it says that the data has been placed over there at that address. Once your transmission is completed, you get a notification on a completion queue saying that it is done with the status like that. If you are familiar with Linux IOU ring, that's pretty much the same idea, just implemented 20 years later. To model the interface for that would require quite a radical move away from BSD sockets, because it just doesn't have anything close to this. Whether we should care about Rocky and various flavors of that, it used to be the niche protocols used in high-performance computing, but today, with the advent of the accelerators and all the craze about all this AI thing, that's becoming quite widespread, and good indications are that it is not going to disappear anytime soon. Yes, over time it has been migrated to run natively over the Ethernet. That's completely separate domain of problems and complexities. We are just not looking into that. Fiber channel, another source of possible ideas, and what fiber channel is used for storage. So if for block level storage, you can have functionality as to have your remote disks being accessible over the network as if they were connected locally to your node. It's a protocol which re-implemented much of the ideas from the IP world by replacing the first letter of abbreviation to F, because fiber channel. Instead of OSPF, there's FSPF there, which does exactly same routing functionality. But what fiber channel got right from the design beginning is integration of naming and addressing. The endpoints, nodes and hosts in the fiber channel network, they have names. It looks like 8 hexadecimal digits, but that is treated as a name. There is a function called name service, which translates the name to the topology dependent identifier. That's an address, that's 3-octet entity that is used for routing. But that's internally. Your application doesn't use that. And it's dynamic. So in a sense, this is an integration of DNS and into the IP world, and that's seen as one common connectivity service. You actually cannot easily get to dealing with a connection on a fiber channel identifier level. If you try, you certainly can, but that's not the use case, normal use case. So having the ability to connect based on the host name and possibly some parameters attached to the host name seems to be well, needed functionality if we are talking about a general interface in the IP world. And even furthermore, if we look at the, say, transport distribution, the dominant part of payload is HTTP based. And it has its own, say, ALPN naming and identification of where the particular service is going to be connected to. Therefore, IP address is becoming more and more as just a local identifier, which might be ephemeral. And what you actually need to deal with the connection is the name. Names are far more stable. QUIC. Rather relatively new addition, but that is one of the mostly visible protocols on the network. If you look into the traffic counting statistics, again, depending on where you look, for example, from a browser perspective, around 2/3, probably even more these days, of traffic coming into your browser is based on QUIC. And that's used between the service edge and the actual content consumers. UDP-based, which models the connection properties, multiple channels, ability to define flexible congestion control and well, quality of service type of parameters there. Ability to move, ability to resume the session in a sense that you can start, establish the session, do an exchange, terminate it, and then restart it faster than if you would do normally from the beginning. It has, again, behind the scenes, this is UDP running a derivative of a TLS, and on top of that, modeling the multipath TCP way of having multiple transport subsessions. Almost all of QUIC implementations, which are probably now in high tens, maybe low hundreds, are in user space. Kernel implementations for operating systems, well, there are prototypes, but that's not, say, something that has been finalized mainly for two reasons. One, the design for QUIC was mostly driven by the browser networking, and their interest was in rolling out the protocol as fast as possible, as fast as practically possible into the field to gain the experience with that and to do rapid reiterations and revisions to that. And trying to implement that in the kernel is not necessarily efficient. The other aspect is, it relies on the TLS, and majority of the TLS libraries are in the user space. So from the perspective of the communication, or basically the interface into the transport, the QUIC-based transport, it brings in probably a uniform mix of functionalities that has been mentioned in previous transports. So you need to have an interface to feed in the credentials. You need to have an interface to demultiplex the subchannels. You need to have an interface to get and set the underlying transport parameters and things like that. So if we try to generalize this in 2 dimensions, if we look across the protocols, the basic requirement is how do you establish a transport session between the 2 endpoints? That's naming. And there's a clear indication that moving away, or at least having more focus on name-based, DNS name-based identification is required. IP addresses, they will still be needed on the wire. However, they are not necessarily need to be visible from the application side as much. There is a need to have ability to signal transport-specific parameters and configurations somehow in a more uniform way. One of the possible candidates for that is a descriptor-based scheme. Basically, your descriptor defines the superset of all transport protocols, and the particular instance of that picks what is needed for that particular transport protocol. Congestion awareness and basically interfacing with the congestion control. This requires another type of the interface which would allow to have a visibility into the current state of the network and possibly interfere with that, try to adjust that. Now, one of the major problems with BSD sockets interface is synchronous. In a sense, you call some particular function and it expects and it will operate until the completion. Yes, if you set your socket to non-blocking mode and it cannot accept as much as you're trying to send at the instance, you will get an error notification, which is in fact not an error. For the lack of a better way of signaling such a situation, it is indicated as an error, but that's not an error from a transport protocol view. That's not an error from the particular implementation point of view. That's just not lack of the way to signal that at this particular instance, I am unable to accept as much data as you want me to send. And an interface which is based on well, sending out something, a message, a descriptor, or some other entity, or actually posting it to some queue and leaving it there and continuing doing something else, and then getting a notification, or actually querying for the notification yourself from another queue, appears to be way more practical if we are talking about the simplicity and to an extent about the performance from the application point of view. You don't need to handle the exceptions. Your interface to transmitting into a network is one point. You send out a descriptor and you either will get notified that it has completed or you will get notified that there is an error. The interface of receiving from a network, again, is querying one particular queue. You can run that in the interrupt mode, you can run it in the poll mode, and it depends how you implement that. But you don't need to deal with multiple exceptions. Oh, okay, say epolla KQ indicate that I have activity on this particular socket. What does that mean? Is there a data, or is that actually TCP session has been closed and I need to handle that as an exception? If we're looking from a data perspective, the equivalent of descriptors needs to say that's really a simple abstraction. And if we have a mechanism to represent the subchannels as descriptors, that probably would be a right way to do. We need to be able to use existing or at least familiar event notification systems. So KQ, epoll, wait for multiple objects. Definitely needs to be asynchronous. Send out something and forget. Don't wait. Don't expect an error at the same instance. So if we look into the requirements and try to group those requirements into some logical kind of units. Integration with naming. So that's probably the most important part here, and say a hypothetical transport connect function which puts in the URL and the context parameters. And the context parameters basically contains everything that is needed for this particular connection to succeed, like certificates, transport properties, address namespaces, routing, whatnot, and provides back you with FD, which represents a connected TLS session, which you then can put into your event handling loop or use it in some other way. Equivalent of that might be to use the queue model, that you have multiple queues, say the control queue, the completion queue, the transmit queue, the receive queue, and you just post different messages there. And depending on what happens, you might get a notification on one or multiple queues saying that, okay, your TLS connection has been established, here's an FD, and here's your buffer at that address with that length, you can use it. The important aspect with new commodity transports is basically dealing with the security credentials. How do you feed in what they expect? Majority from a practical point of view expect a certificate in one form or the other. However, if you're looking, for example, that same TCP/IO, it expects a slightly different type of credentials in a slightly different way. The interface needs to provide that. Yes, that's a niche applicability, but it's broadly used in network control plane environments, and therefore that is also important. Ability to select a path. Most of the contemporary transport protocols, they are multipath available. And it would require an interface to be able to select which particular path, or all of them, or a subset of them, or to select a path over particular restrictions and so on. A very practical example, your cell phone has two radio interfaces. And it may happily use both of them at the same time, and the application might want to control why, for what purpose, and at what parameters. Congestion control, that's an integral part of the end-to-end transport service, and it generally works really well. The problem is that it's not that easy to get insight into what is happening there and to try to adjust that from the application perspective. You can certainly do that from an operating system perspective, but the value would be in having that programmable interface into that, or more programmable interface than, for example, just reading some specialty files and trying to write some values there. Buffer management and ability to predict the network performance. It's not only that you can send something, but how aware the network is about your intentions. You might want to do, for example, certain guaranteed bitrate type of services where you send out something and you want to prevent an underrun, that your transmit buffer is empty. Yes, the current transport interfaces will notify you that the buffer is empty, but that will be too late. The buffer is already empty. If instead it allowed you to set a certain level of watermarks, saying that if my current transmit queue, either on the kernel side or user space side implementation, is below this particular threshold, I get a notification on my completion queue, for example, and I can adjust the rate at which my application is trying to send out something into the network. And by the way, what I've been talking here about applies equally to a user space or kernel space implementation. Technically, the details of how that is done would be different, but from an interface point of view, we are talking about how to interface to transport parameters, and whether that's a kernel level implementation or whether that's implemented in user space and will stay like that. This fundamentally doesn't change the actual interface. How the particular signaling and then basically wire imaging bits on the wire and notifications will be implemented is different, but that is outside of the scope of trying to define such an interface. Ability to mark the data. Right now, one of the limitations for marking what you are sending into the network is per socket. So basically, you set a DHCP value on FD, and all the data that gets sent will be marked by that. What if you want to do customized marking? There are extensions that would allow you to do that, but there is no single interface that would allow you to describe that this particular object, this particular frame, has to have this marking because you want it to be treated differently via the transit network. And the security aspects. How do you authenticate with whom you are talking with, and how do you manage the keys? Plus also subchannels. Well, subchannels, today the reality is that subchannels are kind of given, and they are represented as separate file descriptors. That's not a major problem, but still this needs to be somehow integrated into the overall interface architecture. If we try to layer that and draw some diagrams here, two parts. The transport service parameters, so basically it's a pre-configuration. That's a new concept if we compare that to the BSD sockets. We pre-set up the connection properties, like that same mentioned certificate, routing parameters, quality of service parameters, and things like that. And only that, and get a context identifier for that. And then the connection is established by giving the name and referencing that context. And then there's a third phase, which cleanly shuts down the transport connection. Then, if we are talking about the backwards compatibility, the BSD sockets and similar implementations could be modeled on top of this interface, or maybe could be left in parallel without this unification. That's an open discussion, and sometimes that gets quite a heated discussion. Well, this proposal is coming mostly from IETF side, the standards organization, which tries to standardize the protocol, both the protocol mechanics and protocol wire image. And the views there might not necessarily be practitioners' views that use those interfaces for actually building and using, building the applications and using the network. So therefore, it might look contentious, it might look unrealistic, and therefore is the reason for this talk. It's basically to socialize what is happening on the network side, network engineering side, with the software engineering community, and to get a feeling whether this is completely crazy or this might be something reasonably useful. So you have different subinterfaces for configuring the parameters of the transport sessions and then for handling the events. Then the actual implementations of the transport protocols, and the important part is on the left of that gray rectangle, the DNS, which is integrated into the transport layer. So you don't directly deal with IP addresses anymore as you do with the BSD sockets. You basically deal with names. IP address can be treated as a name. And then below you have the existing infrastructure of packet layer, the packet transport layer, which just treats everything as a packet. Now about the events. The important aspect is basically move away from a synchronous call model into the synchronous queue model, where you post something and notification comes via a different channel. Ability to select a path out of the multiple available ones seems to be important, and that needs to be somehow standardized. This mechanism may allow you to have one single control point from your application point of view. Both the transmit side and the receive side might be visible from the same queue. And therefore, you have one point which directly interacts with all of your transports, and in a normal operation and in exceptions. And it's also important to have ability to see what is happening on the congestion control side. So if we try to visualize that, your application has multiple queues to which it sends or receives something from. And again, the data part of BSD sockets can be implemented on top of that, or maybe left aside as a standalone subsystem for the use cases which don't require such functionality. And from a semantics point of view, you have three major operations: transmit side, receive side, and exception or error notification. So what's the current status of all of this? The reality is that most of the transport implementations, they have been defined keeping that particular transport protocol in the main context. The rest is while important, it's not of the first importance, and therefore there is no single kind of end-to-end view of how multiple transport protocols can combine. That is the reason why you see very different interfaces. That's the reason why you see very different approaches to event handling. This is just a reality in which IETF operates. The working groups there are focused mostly exclusively on their own tasks, defining yet another transport protocol, which is certainly fun, but not spending too much effort in trying to integrate all of that. So the common transport interface was such an effort. It has been concluded now, has been going for like 8 or so years, trying to define a model of the all-encompassing interface into different transports, trying to derive common properties and trying to define what might be of practical use. One of the problems with this particular instance was, and that's not the first one, there have been previous attempts in the IETF as well. But the particular problem with this is that it was heavily academically influenced and driven. So basically the key contributors, they have finished their PhDs and move on doing some other things, and the interest into trying to define the universal interface has slightly declined. In particular, I'm talking about the TAPS, Transport Aware Packet Services. NEAT is another new extended API to transport, if I'm not mistaken. This is another initiative driven by yet another university. This is mostly outside of the scope of IETF, to define something similar but in rather incompatible and different way. And also, if we're looking into the network system vendors and operating system vendors, there are attempts to define certain vendor-backed interfaces. Some are successful, some are less so, but again, this is fragmentation. The important aspect to remember when talking about IETF specifications, the fact that there is an RFC published doesn't mean that the world cares, and it doesn't mean that that will be implemented and productized. Basically, it specifies a certain instance of thinking that got approved by the IETF process. Whether that means that this solves practical problem in the field in a practical way, no, that doesn't mean. And that is not an uncommon situation that you... why I'm showing this? What happened? Apologies for that. I need to go to where I left. Right. And that's not necessarily what the industry will implement. Therefore, if we are talking from a perspective of the interface into the transport in the context of a programming language, it might be a good attempt to try to define a practically usable interface into the network's transports, not on the IETF side, but on the specialty languages side. Because that is way closer to how that could be used in reality. And there are some attempts to implement the TAP specification, for example, for C++29 as an experiment. There are some attempts to try to define a different universal transport model interface. It is still way too early to try to talk about that with specifics. And the main reason why I'm talking about this is to gather the feedback from the field. If you think that this is a problem, and if it is a problem, do you think it is worth trying to address? And whether the effort put into trying to address this would offset the costs that would you have if you continued to use the current interfaces into the transports. So this basically leaves part one, which talked about the interaction between the two applications, two endpoints, leaving aside the rest of the network. The second part is the interface into the network topology. And when I socialized that with a few people here prior to going on stage, the feedback was, Ignas, are you crazy? This is really not the crowd that would be able to understand majority of that. Therefore, part 2 is really trimmed and light. It is about how your application can try to control the topology of the network, the path selection over which particular way the packets will go through. How do you choose the destination exit out of your domain and not necessarily your domain? And in what interface that could be done? So if you look from a network from a slightly different angle, it's no longer a dumb pipe. It's an intelligent and programmable entity which has quite a few elements, well, routers, network elements, which are not necessarily visible for you if you're looking only in a transport perspective. But inside of that, basically, it's a distributed database running dedicated and quite complex control protocols among themselves, trying to synchronize the topological view of both the network itself and its external connections and what kind of logical instances are used there. One of the possible options is to basically connect your application to the control plane of such a network and get the visibility into that. Well, but if you read the news from time to time that researchers crafted another BGP message and disconnected half of a global internet with that, first thing, you don't want to do that. Second thing, your network provider will not allow you to do that. The other aspect is what you can control by this. Suppose you want to connect your browser to some HTTP server. Do you care over which particular path your request comes and the response comes back? Probably no. However, if you are dealing with, say, streaming video content or sending out some localized responses or doing some really low latency network connectivity with specific requirements over which path it can go, over which path it cannot, and that might be regulatory requirements. You might see a lot of need in trying to control from your application locally without a connectivity into the network control plane, how to influence the actual path that your particular payload will take. So, possible options. We already ruled out running the control plane directly to the network infrastructure. Not going to happen, both from a practicality point of view and from a complexity point of view. Network control protocols are really complex, and implementing them in a credible way takes quite a lot of effort. Now, this leaves an option for having a specific signaling between the host or the application generalizing and the network edge. And this is the current model. It's not a new concept. Like in previous century, ATM had a rather similar approach to that, where you can, it worked like pre-selecting multiple virtual circuits and then the application actually choosing on its side where to send the particular traffic to. The way how that works today, as ATM moved to history, the way how that works today is basically by selecting a stack of identifiers, and what is used as a technology, whether that's MPLS, segment routing derivatives, or some other custom protocols, doesn't matter that much. As long as there is an ability for application to signal explicitly that looking into this diagram, first it needs to go on the upper left, then it needs to go to the lower right via this particular link. You basically put a stack of instructions that you packet go first there, then from there you go over there, then from there you go over there, and you go to the exit. And this is the source which controls that. It's not the network inside. You don't need to mark the packet somehow. You don't need to do some kind of deriving the policy out of the incoming traffic stream in order to route those. No, your application selects, depending how that is implemented, as a set of instructions. It might be multiple destination addresses, it might be multiple labels, it might be multiple of identifiers that is transported into the network edge and then is spread out, or actually not spread out, but it is already pre-set up in the network and it is just forwarded. The overall technical term for that is network programming. Again, not a new thing, has been in deployment for a couple of decades in various formats. Long time ago, this has been offline, where you pre-select a topology and pre-configure the devices, and you can use that. Today, we see mostly far more of the dynamic state programming, where you don't touch the configuration of the node at all, because that's complex and fragile, where you simply feed in the state into the network elements, saying that now this particular identifier means that incoming packet on this interface goes over there, and incoming packet with another identifier incoming on this particular interface means that. Right? From a protocol mechanics point of view, this is mostly a solved problem. The very unsolved problem is how do you represent such a topology and how do you feed that into application, provided that a lot of this is very, first thing, vocal, in the sense there's a lot of information. The second thing is very vendor proprietary information. This is a reality of how the network platforms are implemented. All of them, they do mostly the same functionality, but in a very different way. And in order to influence how they do that, you need to be vendor specific. So the possible approaches to that is you need to abstract the topology somehow. So you have network elements, the routers, you have the links, you have identifiers of those on those links, then you have paths. Multiple layers of this, you feed that aggregated into some entity which builds the topological view, and then your application can request to that topology saying, I want a path from this interface on this node to that interface on that node, going via this link, but not going via that link, having capacity like this, and having, for example, tunneling properties like that. Request gets fed in, network state is changed, and your application can send out the payload, which traverses over the topology which was requested. There are multiple approaches. Again, I2RS, this died in IETF a decade ago because it tried to address too much. There are Google-specific implementations. There is Netlink. Yes, Netlink, the same Netlink which is used in Linux, can actually carry these types of protocol elements. The reality today that such systems do exist quite universally. All of them are vendor proprietary. All of them are mostly used in limited domains, and they solve practical problems which are within those limited domains. We probably need to think about such an interface, but that's second priority. Once the transport interface is either solved or we have an indication that we don't need to solve that problem, we might think about a more complex thing of how you deal with the actual network topology. About the use cases of this, basically, they all relate to traffic engineering. That can be a general term of traffic engineering, to steer the traffic by means other than destination. So indicating that this particular application can go via the left side or it must go via the right side for various reasons. Technical or non-technical, ability to reserve certain resources, ability to have protection, and ability to have to validate whether the actual logical connection is present within a network and is operational. And all of that, in ideal case, needs to be set up dynamically. This leads to the third part, the discussion. And yeah, I would be interested in hearing your feedback, especially about the first part. Let's leave the second one just for say, the curious exercise. Do you think that a common transport interface would help you? Do you think this? Well, do you feel a pain, say, in your daily activities? Whether that's something worth investing time and addressing? If we are talking about, say, from a pragmatical deliverables from a C++ perspective, we are talking about some form of a library. The library that integrates with the existing concurrency mechanisms, and a library that provides more or less universal transport interface for today's commodity transport protocols. Again, if you don't use most of those that have been described here, probably that wouldn't be a limiting factor. because others equally use different transport protocols for different purposes, right? Therefore, this whole discussion about the universal transport protocol, that's what I have from my side. Now, I guess the microphone line is open. Any comments, any feedback, any questions, any gifts and bribes? I'm all open.
Thank you for the talk. Question. You mentioned multiple protocols, all of them peer-to-peer, as I understand. Do you consider multicast?
Most of them support multicast.
Okay.
In different ways, in different capacities, right? All datagram ones support multicast, like from out of the box, right? It's not a restriction for them. Trying to define multicast operation on the stream-based protocols in a unidirectional way, that's possible, and some of those do support that. That's not necessarily a commodity use case, but on the other hand, multicast inherently is unidirectional for practical purposes.
Yeah, thank you.
I would say for the data interface, one of the big things that I've had to deal with on an embedded and mobile type of scenarios would be trying to discover if I'm not receiving data, is that because the network is down? Is that because packets are being dropped somewhere? And I don't have any sort of system interface to query in TCP in particular. When was the most recent ping to the next peer? Did I receive a ping from them? And the closest I can get is a timeout on the data, which is not necessarily a timeout on the control stream itself. And there's a lot of other protocols that kind of help solve that. I could re-implement the entire TCP stack in user space. And at that point, why not just look at QUIC? Like you mentioned, current implementations of QUIC kind of do that because they're in user space. But on the other hand, there's other implementations that I would hope I could get that kind of visibility, but I'm not aware of, what is the system interface for those? So
there are two parts to this. One, in order to get visibility, you need to have something that gives you that visibility. And if on a hypothetical TCP session there's nothing being sent back or forward, you won't see anything. This is a whole other domain of OEM, basically operations and maintenance of tunnels, interfaces, and connections. Generally, if you want to know that your connection is alive, you need to send some form of probes there. BFD in IP world and MPLS world is one. Ethernet OEM in the Ethernet domain is one. MPLS OEM and the whole machinery there is another one. The idea here is that into abstraction of the connection, be it an interface, a tunnel, or just a TCP session, you inject something that is received on the other side, but that is not treated as a payload. And then you can have, basically the other side will have visibility. One of the BFD operation modes is it basically can send echo. In a sense, you send out from yourself a packet to your neighbor addressed to yourself. The other node will loop it back. And this way you will know that you have bidirectional connectivity. There are other OEM protocols that operate in similar ways, right? So the problem of getting a notification, yes, it's an open one. You need to define the interface, how you get a notification. Because there are different encapsulations, there are different interface type of properties, and they will provide a different type of information. But the other thing is you need to have something that generates that probe information. And this is the second part. Basically, you need, for example, you set up a connection between the two endpoints and you tell your edge network nodes which are the first and the last hop routers for your connection to start a BFD session among those endpoints. This way, if you get the feedback from a BFD session that it is up and running, you will get an indication that your tunnel over the network infrastructure is up and running. It's not enough. You also need to run from your host, injecting the probes into the actual tunnel to understand that the endpoints of the tunnel are connected. And then if you look deeper, you need to have probes which verify that your tunnel endpoint is connected to the endpoint which it is supposed to be connected. There's a notion of connectivity and continuity. So basically, continuity is that you have a path, and connectivity is verifying that you are connected to the right endpoint. It's a complex area, way more complex than just a transport interface. Generally, it works. It's not interoperable. Again, we are talking about the limited domains. And the grand vision of the global end-to-end OEM, yes, in OEM days, that was a grand vision. OEM moved nowhere. To an extent, we still have a requirement for having end-to-end OEM, but not as acute as it was previously. Because today we have far less end-to-end global connectivity, because majority of your traffic is local. It's basically the content edge to your eyeballs, and that's it. And that's where the majority of both from a technology point of view, complexity lies, and from a capacity point of view. You don't have that much, traffic or requirement to have the connectivity between different edges of the world, right? Basically, the connectivity patterns have shifted.
Thank you.
But apart from that, well, excellent question, and this is a fascinating area to go deep into. Yeah.
Hello. I appreciate you trying to tackle this problem, which kind of makes my head hurt, like when I try to think about it. I'm wondering if, I guess, not having thought about this problem for very long, I'm wondering what are you seeing that's appealing to you from a language perspective? Like why? I guess my question is why do you think it's good to put this interface in the language level instead of, for example, at the OS level? Just to use my company as an example, we program in a lot of different languages, but we only care about Linux, for example. And I wonder if you could just achieve 80% of your desired outcome.
All right, so just to kind of amend a little bit, I'm particularly not talking about the language, but the library. So right. Yes, you use the word language in a different context and a different meaning, and I understand your question. So if you try to define the operating system-wide interface, that first thing rules out the user space implementations mostly, because then you will have to do something like a tunneling back to the user space. Second thing, you will need to, basically persuade the operating system to implement that interface. Whereas if you try to do that as a library, right, you use your application on top of the operating system and you use the interface that operating system provides and it works. That's one scenario. The other scenario is that you use it as a library and you implement it in your application. You are no longer dependent on the operating system as long as the library can talk to the interfaces provided by the underlying operating system. It's from the pragmatical point of view.
So I'm just kind of thinking about, let's say BSD has a set of socket options, Linux has a set of socket options, and then Windows maybe has their own set of socket options. So there's still some portability concerns when you try to migrate one library to another.
Yes. So the goal is not to have something universally, globally uniform. No. And it's not the goal of the interface from a definition perspective. You have interface flexible enough to be able to express the requirements into the transport protocols. Whether all of them will be implemented in all languages, on all platforms, no, definitely. Let's look realistically, it won't be, right? Starting from event handling, right? Wait for multiple objects is a very different semantics than KQ. And that is not going to change. Therefore, the importance from a library point of view will be to provide a rather stable or superset interface to the application. And only the portion of that superset interface will be actually implemented for a particular instance of the language and a particular instance of the operating system.
Okay, thank you.
So you mentioned earlier in the talk about sort of the submission queue, completion queue thing that also looks a lot like IOU ring. Mm-hmm. Would it be reasonable or interesting to think about kind of a low-level library that implements that in a very generic way that might wrap both of those things, that you could essentially use the same idiomatic type programming style for IOU ring and networking?
Well, I will probably comment on that. That IOU ring looks a lot like the queues described here, because IOU ring came noticeably later than, for example, InfiniBand queue pairs and that same fiber channel abstractions. It's not about arguing who was first. There is a similarity in a form of basically you have the request and completion queues in IOU ring. Whether that can be extended, probably, but again, the main limiting factor in my view would be that it is a kernel-based interface. So basically that would rule out the user space.
But I could theoretically I could create a library generic enough that would allow you to touch the kernel level interface and then also the user level interface.
Whether that could be done, not arguing, certainly could be done. The question, at what cost and whether that's practical, right? To have a common interface which looks like IOU ring only, given the amount of functionality that IOU ring supports today and well, kind of looking into perspective of what it will eventually, probably yes. But again, U-ring is specific to one particular operating system.
I'm thinking more in terms of like the general idea of I have a submission queue and a completion queue, and that I can do a lot of things with that specific type of interface, kind of the same way that I can do a lot of things with like the file descriptor interface from POSIX, right? Would it be interesting? And each of these things, like you have once you develop skills with POSIX, you get used to it. It's easy to sort of like predict how things are going to work and write your code. And when you're first exposed to the submission completion queue thing, it takes a while to sort of get up to speed. So I was wondering if it might be useful to sort of generalize submission queue, completion queue in some way where that becomes kind of another standard type of idiom at a lower level that people could use for many different things.
So generalizing it as a concept, definitely yes. Generalizing that as one common implementation, so in a sense you have one descriptor which goes into the IOU ring queue, and then everything goes through that, probably no. Okay. I wouldn't see that too practical. Well, basically, first thing is a single point of failure. Second thing, it's additional complexity. Basically, you multiplex a lot into the IOU ring, and then you also need to demultiplex it on the other direction, right? So that seems to be like an extra work, which is probably avoidable.
Okay, thanks.
Yeah. Hi, thank you very much for working on this, by the way, because it's a terrible problem.
I feel your pain.
Yeah, that's it. I'm not sure what I want. I know things that I don't want, though. I don't want to end up with an API in the standard that I have to tell everyone not to use, which is where we are essentially with our thread APIs, that they're too uniform to the extent where, like, I've got operating systems where they just do the wrong thing. And they're tempting to programmers because they're there in the standard, so they must be the right thing. It's like when I've been doing porting work, for example, it's AIX, horrible in all respects, Unix as implemented by people who've never seen it. The default stack size for a thread on AIX was like 64K. And there was no way in the C++ standard APIs to change that because like there wasn't a uniform way across everything we knew. So we standardized what was uniform across a lot of things. And that just turns out to be bad for everyone. So no, I don't want a universal network API that's good for all. It's like, I don't think there actually could be such a thing. There's too many corners of the space that are just different for how you might want to ask for something to be done or represent it, that one API, at worst case, it devolves into, here's a JSON description of what I'd like you to try and do. Please go out and try and do it. And that's not useful. But on the other hand, I do think we should be much better for common user businessy application kind of network requests where it's like, I want all the data at that URL. Please just give it to me until it's like, I know that lives at a much higher level than what we're talking about here, but it's like there's somewhere, down at the bottom, there are kernel interfaces or maybe user interface spaces, and hopefully we can come up with something common enough in the middle that we can program to and still have to swap out the bottom. But it's like, but thank you for working on this because it's a wicked problem.
Right, so thanks for kind words. Now, kind of trying to summarize this, and I see the clock blinking, but I guess this is the last session, right? So nobody's going to kick me out of the stage, fine. This is certainly not for everyone. If your application is sending 2 syslog messages per day, you probably don't care. If your application sending full line rate 100 gig E 24 hours per day to multiple destinations, you already have mechanism how to control that, and basically it's a solved problem. You use your own transport and you are happy with that.
That's
mostly.
Yeah, I would not say it's a solved problem, but yeah, it's a understood problem we're managing now in various ways.
Yeah, and you're talking most probably about a limited domain where you have full control, you can do whatever you want, right? And that's addressable problem, right? Solved problem was the wrong word from my side, but it's addressable problem. However, if we are talking, take for example, a hypothetical example, web server vendor. Well, somebody who implements an HTTP server. Right, and the HTTP server happens to be able to handle like a few tens of thousands of requests per second. Not a very large number, but not a small number. Well, there is
more than a toy, but yeah.
More than a toy, yeah, and it takes a little bit of effort to handle 10K requests per second, even from a network interface perspective. Well, you need to know how to do that. Therefore, if this can be kind of simplified, probably that's the target audience. And again, the example of the HTTP servers, well, all of them, HTTP3 is QUIC based, right? So that's basically a HTTP over QUIC. All of them implement QUIC in their own way because they need to integrate that into their event handling infrastructure. Does that work? Yes, that works. Is it painful? Yes, it's painful. Can this be avoided? Probably if, for example, a language allowed for an easy to use and practical to use library abstraction for this.
Yeah. Thank you.
Right, thanks. Thanks a lot.